Good afternoon, everybody, and thank you so much for joining today's briefing, where we'll be discussing a forthcoming guidebook on coal to hydrogen opportunities and challenges. I'd like to thank a number of different people for making this happen today, for BCS and the BCS team who prepared this report, as well as the Department of Energy, Office of Fossil Energy and Carbon Management, as well, and the National Energy Technology Laboratory for making this possible. Today this briefing will be moderated by Andreas Thanos, who's a policy specialist with the Massachusetts Department of Public Utilities. He is also the chair of NARU's staff subcommittee on gas, and I will turn it over to him for an introduction.
Thank you, Jasmine. Welcome, everyone. We talk a lot about hydrogen lately on both sides of the Atlantic. Japan, wherever you look at, everybody talks about hydrogen, and hydrogen is a fuel that seems promising. The questions are, where do we get the hydrogen from? And this is what Mike is going to talk about today for hydrogen from coal. Mike has an extensive background in clean coal, and he has also been the CEO of the highly visible Future Gen Industrial Alliance. Mike is going to talk about the processes, the benefits, but one thing I would like you to keep in mind is that this is not a must-do approach. Like I said before, hydrogen can be produced from different sources. Coal is one of them, and Mike is going to go into the details that are very, I guess, extensive. I read the draft, and it's a very comprehensive report that was, as Jasmine said, it will be forthcoming. And before I go on again, I would like to repeat, do not take this presentation and the white paper when it comes out as a must do. This is part of a toolkit and the options that both regulators, the industry, and the world at the end of the day has in its possession. Mike, thank you.
Good afternoon, everybody, and thank you very much for joining us today. As is mentioned, the guidebook itself, it covers a lot of topics. I'm going to be touching on them very briefly today, not going into much depth. If you want to learn more, by all means, you can just get this guidebook when it comes out. I'll be talking about coal and hydrogen, the uses of coal, and how you can make hydrogen from various sources, and then talk about carbon capture and sequestration, and conclude with some recommendations and some issues. Okay, let me go on. Let's first talk about coal, which some now say is a four-letter word. But at the same time, we have to remember that the United States has huge coal reserves. In fact, we have over 260 billion tons of coal reserves in our country, which is 28% of the global reserves. But at the same time, there's been a 48% decline in coal production over the past 12 years. That's it, our national resources staying in the ground rather than being used. So the jobs have declined in the coal industry. In fact, 130,000 coal jobs have disappeared since 1985. At the same time, coal plants have been retiring. In fact, more than 100 coal plants have retired or been replaced with natural gas since 2011, which is 95 gigawatts, and another 25 gigawatts are scheduled to be shut down by 2025. In fact, this kind of touches me on a personal basis because early in my career, I was involved in design and construction of 1,300 megawatt plants, the largest plants at the time in our country, very efficient, supercritical plants, had all the state-of-the-art controls. Those plants are being shut down now, so it shows the rapid shift away from plants. When we built them, we would thought they would be lasting for 40 to 60 years or more. Now let's talk about an 8-letter word instead of a 4-letter word, hydrogen. What is hydrogen? Hydrogen is the most abundant element in the universe. It has the highest energy content per unit weight and the lowest density of all fuels. The natural form is as a compound. You don't find a natural form of H2 in the atmosphere. Therefore, it must be converted from a compound to be usable for combustion, which I will get into. There are a lot of advantages of using hydrogen. It's a versatile fuel that offers a path to long-term economic growth. It has the potential to meet 14% of the total U.S. energy demand without emitting CO2 by 2025. It's a sustainable fuel for transportation, electricity, heat for homes, and many other uses too. And it enables a near zero emission use in transportation, remote power, and portable power applications. In fact, with hydrogen, you can have an integrated approach from all energy sectors if you want to realize the full potential and benefits of hydrogen. So let's talk a little bit about the three ways that hydrogen is produced. One is called electrolysis. Electrolysis, you can look at it as a battery. You take water, put it in like a battery with a cathode and an anode, and it converts the H2O in the water through electricity. It breaks it into hydrogen and oxygen. Right now, this is the most expensive process that's used for making hydrogen. I'll show that in a subsequent slide. Another one is called steam methane reforming. In that, you take CH4, natural gas, you heat it with water, and it forms carbon monoxide and hydrogen. And then you take the carbon monoxide and you run it through what's called a water gas shift reaction. You react that with water, and that forms carbon monoxide and additional hydrogen. Right now, this is the most common way to produce hydrogen. A third way that we talk about in the report is gasification. In gasification, you take a carbon-containing material, coal, and you put it under pressure, you feed it in a reducing atmosphere, and you convert the carbon to carbon monoxide and hydrogen. I want to point out this is not an accurate chemical equation, but I do want to mention that the oxygen is in there because there is oxygen in the process. And then you take the carbon monoxide, you go through that same water gas shift reaction, and you can convert that to concentrated CO2 and hydrogen. Now that is a water shift. That's how you're producing gasification. I'll go into a little bit more of that in the future. So this also has the potential to be the least expensive process for making hydrogen. The comparative cost of hydrogen production is here. You can see that on the steam methane reforming, it's roughly $2 per kilogram. Coal gasification is lower. If you do coal gasification with biomass, it's somewhat higher. At the same time, it's about 3 times higher if you use the electrolysis I was talking about. But this curve shows the relative CO2 emissions. You can see how the CO2 emissions go up significantly with gasification, but then if you do it with biomass or electrolysis, depending upon the source of power used, you can have 0 emissions when making hydrogen. So currently, the fossil fuels is the least expensive source, even with CCUS, but we still have to address the CO2 aspect of that. The current hydrogen production in the US, as I mentioned, is dominated by steam methane reforming through natural gas. It produces 96% of the hydrogen in our country. You can see that electrolysis is a trivial amount. Worldwide, 76% is still by steam methane reformation, more by gasification, mostly in China, but still a very small amount by electrolysis due to the higher cost. Let me talk a little bit about coal combustion. What happens when you burn coal? The main elements of coal, carbon, hydrogen, oxygen, nitrogen, and sulfur. When you mix that with oxygen and the nitrogen in the oxygen, you form carbon dioxide with the carbon, you form water with the hydrogen and the oxygen, you form NOx, NO2, NO3 with the nitrogen, you form sulfur, SO2, SO3 from the sulfur, and ash with the fly ash or bottom ash. Of course, the outcome of that is heat. So what happens in a boiler? You take that, put it in a boiler in a power plant with feed water to make a steam turbine with that heat from the combustion of coal. But now you have to put these elements on the back end of the power plant, a SCR, a selective catalytic reactor to remove the NOx, an electrostatic precipitator or baghouse to remove the fly ash, an FGD, a scrubber to remove the sulfur, and then a CO2 removal system, typically using an amine solution to take the CO2 out before it goes to a stack. Most power plants right now do not have the CO2 removal. So from here, the CO2 associated with coal combustion goes to stack and to the atmosphere. But PC with a pulverized coal plant with CO2 removal does not produce hydrogen in the process. But this is the traditional way that they burn coal in order to make power. Let's talk about gasification. In gasification, you take coal, you feed it into a gasifier. In the gasifier, under pressure, typically, you have that reaction I was talking about, where the carbon is converted to carbon monoxide and hydrogen. You cool the gas, and then you put it in another system to go that water shift reaction, where you take the carbon monoxide plus additional water, and you form carbon dioxide and hydrogen. It's under pressure. So now you feed it through two additional boxes. One gets rid of the sulfur, and the other you can go through a CO2 removal process. Because a gasifier is under a higher pressure, the technology used to remove the CO2 is much more efficient and lower cost than it is with a conventional plant. You need an air separation unit to remove the nitrogen from the air, which allows a lower volume and a more efficient gasification process. The steam generated feeds what's called the heat forms what's called a combined cycle. There's a gas turbine and also a steam cycle. That combined cycle provides a much more efficient way to generate electricity than with just a steam cycle in a conventional PC plant. Just want to touch on, as a reminder, this is the byproducts of the difference between combustion and gasification. The carbon goes to CO2. It's stable, it's much more difficult to remove. In gasification, it goes to carbon monoxide, which you can react with hydrogen, with water to form the hydrogen. The hydrogen goes to H2. The nitrogen in combustion goes to a form of NOx, whereas in gasification, it goes to ammonia or pure nitrogen. The sulfur, instead of becoming a relatively stable sulfur oxide, goes to hydrogen sulfide or COS, and the water goes to hydrogen. And the difference between these is significant. In gasification, when you take the elements, in fact, you take a good chemical engineer and you give them these different compounds, and they can do virtually anything with it, which is why if you see a gasifier plant or you see a chemical refinery, you see an abundance of different bottles and processes, because under pressure, you can do quite a bit more, which is the advantage of gasification in doing this. Now, what do you do with the hydrogen? This is a view from the Department of Energy, which they see as a hydrogen economy. In the middle here, this is where hydrogen is generated, either through one of the processes I'm talking about. The hydrogen can go and feed a whole abundance of different systems, which I'll touch in a moment. At the same time, you can generate power with the hydrogen to feed the grid or go back and help with the formation of hydrogen. At the same time, the source of electricity can be either from conventional sources or renewables, nuclear, fossil, or so on. It can also feed the gas infrastructure back and forth. It's a wonderful integrated approach that the DOE has. This is called the H2 Scale Initiative, which provides a vision for how hydrogen can enable an energy pathway across applications and sectors in an interconnected energy system. What's the demand for hydrogen in this country right now? Mostly it's used for oil refinery, chemical production. It's used for metals, electronic glass, used for food production. It's used for transportation to a very low extent, building, heating, and electric generation, but to a lesser level. Right now in our country, the demand for hydrogen is approximately 10 MMT. But the scenario is that eventually we can triple that. Can enable over 30 MMT of hydrogen demand in industry in all the different uses. How can that happen? It can only happen through R&D, by coming up with meaningful R&D targets and meeting them and looking at the necessary market transition for barriers that have to be overcome. Every report has to include the cost of technology. And this chart shows the relative cost of technology. I'm not going to go into that, but I do want to point out an important thing, that a lot of these, PC with carbon capture, even IGCC with carbon capture, it's natural gas combined cycle with carbon capture, these are estimates. These costs are typically developed what's called a FEED, front-end engineering and design study. They're studies, they assume a lot of assumptions, they assume a lot of estimates. With the first-of-a-kind technology, usually it takes 3 or 4 plants before you truly have a mature plant that you have a good handle on the cost of that plant. So whenever you're looking at the cost for a new plant using new technology, look at it with jaundice. Get some consultants to take a look at it, to critique it, and make sure there's sufficient contingency and sufficient realism behind it, because there's a good chance it'll be low, which I think history has proven with many new plants. Talking about carbon capture, that's discussed extensively in the report, but I just want to touch on it. The first one is called post-combustion, which you use in a pulverized coal plant. And That's that box at the end. It's a flue gas separation system where simplistically you can look at it, a box where they take what's called an amine, and the amine is fed into a reactor, into the flue gas. It mixes with the flue gas, and at a temperature of about 100 degrees Fahrenheit, that amine will absorb the flue gas, the CO2 in the flue gas. Then you pump it into another bottle to heat it up to about 200 degrees Fahrenheit. So you cycle it between 100 degrees Fahrenheit to capture it, 200 degrees Fahrenheit to release it. You recirculate it. The high cost of that and the challenge are two things. First of all, it's called a temperature swing. And that temperature swing of 100 degrees, it costs a lot of energy. It can take about a quarter of the output of the power plant away in being able to do that. A lot of the research and development has to do with reducing that temperature swing, which would make the process more efficient. There's also attrition. There's loss of the amine in the process. They got to look at amines, which would tend to have less loss to it. Oxy-combustion, just want to touch on it. It's another technique that's used in the pulverized coal plant to recirculate the combustion exhaust, increase the CO2 concentration. The higher the concentration of CO2, the easier it is to remove from the process, the lower cost it is. And in pre-combustion, gasification, where you take out the CO2 as I showed, well, the carbon as I showed, prior to the combustion of the hydrogen. If you do that, I mentioned that box there, typically in a gasifier, they take what's called a pressure swing adsorption, where they would take a solid particle, an adsorbent, and put that in the presence of the flue gas. The adsorbent would actually absorb the CO2 under pressure, take it, put it in another chamber to depressurize it. At lower pressure, it releases the CO2. Once again, it's called a pressure swing now instead of a temperature swing. And the challenge with making those more effective is two things: reduce the temperatures, the pressure swing, and find a sorbent with much less attrition that will last much longer. So those are basically, I just touched on that. There's more detail on that in the report. What do you do with the carbon capture, with the carbon once you've captured it? This is a DOE diagram showing that if you take the point source capture, you can take it, you can put it in geologic storage, pump it down in the earth. There's been a lot of research about that. The advantage is you can basically store it forever down there. Two disadvantages. First of all, it's regional. Not all sections of the country have the geology conducive to good geologic storage. The Midwest and the Midwest Basin and the Texas basins are probably two of the most robust areas for carbon sequestration. Take it, and the biggest use now is for enhanced oil recovery, where they can take it, pump it into oil wells, change the viscosity of the crude oil in the ground, and make it easier to extract to improve the performance. That right now is the biggest use of carbon dioxide that is captured. And it can also be used for other processes. I also want to touch on there are other ways to capture carbon that the DOE is looking at. Terrestrial capture, which is absorbing from air. There's terrestrial storage, trees. The biggest example is the rainforest in South America. So there's an integrated approach. In our report, we talk more about that. There are many potential utilization streams for CO2 shown here. The DOE has a lot of research and development. And I don't want to go into details, but I want to pass a message on, and that is to look at the huge quantity of CO2 that can be generated. A 1,000 megawatt plant would generate approximately 6 million tons of CO2 per year, and that's from a single 1,000 megawatt plant. So if you look at all the plants together, that is gigatons of CO2. So while there's a lot of interest in using it for smaller applications on a macro scale, if we are to reduce the CO2 in the environment, we need to focus on the mega scales rather than the macro scales. That's where the money has to be in order to advance the reduction of CO2 in the atmosphere. So what are the challenges associated with carbon capture and utilization? It's very capital intensive. It's got a high parasitic load, reduces the output of the plant. It has a higher operating cost. The technology and operational risk, because it's still a relatively new technology. And there's legislative uncertainty too. You know, should you invest in CCUS? Will coal allowed to be continued to be burned? Will there be a carbon tax? Can you store it? So there's big issues that have to be done. There's uncertainty in the revenue stream associated with CO2. I mentioned the main use is enhanced oil recovery. In one of the case studies I'm going to touch, you can see how that can become a real issue. And there's a liability potential of CO2 leaks. I mentioned the underground storage. That I believe it's safe. Geologists convince us that it's very safe, but it's the obligation of industry to convince the general population that it's safe to pump CO2 in the ground beneath them. We cannot assume the public's going to say, no problem, we trust you. It's up to industry in order to convince people and demonstrate that it's safe. Absent that, there's going to be a lot of issues with respect to the potential liability of CO2 leaks. So what's the quandary for the regulators? Of course, their job is the protection of the ratepayers. At the same time, how do they handle the risk-reward allocation? For every risk, who should get the reward? But we need new technologies to move on, to continue to improve our environment and our lifestyle. And there's a long lead time for major capital projects. So a decision they make today might not happen for up to 10 years. So let me put it another way. What are the risks that have to be looked at? There are technical risks, the performance of a new technology, the guarantees for new technology, the availability, meaning how will it run all the time, or will it be down with shutdowns quite a bit? And what's the schedule? Can they truly have their arms around the schedule for a new plant? I'll get into that in a second too with the case studies. There's cost risks. I mentioned there's cost uncertainty with new technology. With the long lead time, escalation is always an issue. What do you assume as far as the annual escalation? For the past several years, it's been low. Inflation's been low. Back in the 20 years ago, inflation was going crazy with steel prices and commodity prices and so on. It's hard to understand that, and who's going to take that risk? There's costs of redesign. As with something new, you've always got to make changes, and that's a big risk. And the market prices, okay? When you come up with that, what's going to be the market price of the electricity, the hydrogen, the CO2? There's market risk, and when you're looking at over a decade worth of planning, how can you accurately come up with those market prices? And there's regulatory risk. It takes a long time for the approval of these projects. You'll have interveners. Whether you have a good or a bad project, you can know one thing for certain: interveners will be coming in and wanting to have their say. There are many policy changes. Every time there's a policy change, it can impact the schedule and the cost. The biggest example is that when they were building the nuclear plants, there were a lot of policy changes. There were changes in codes and standards that caused design, redesign, and delays in the project. And finally, changes in law. Is there going to be a carbon tax? What's going to be the law with respect to emissions and so on? Those are big risks. So let me show it another way. You have all these risks. All those risks translate into dollars. And there's a tug of war. Is that up to the owners? Is it up to the users, the ratepayers? Is it up to the equipment suppliers? Who is going to take on those risks? It's always an issue, but it must be addressed before you can move technology on. Let me just talk about some of the other projects that I mentioned in our report. One is called the Petronova project in Texas, $1 billion project. That project was a 240 megawatt slipstream, which operated from 2017 to 2020. A very successful demonstration of carbon capture from a conventional coal plant. It became uneconomical when CO2 prices, the main output of the CO2 was to sell it for enhanced oil recovery to the oil companies. But when oil prices plummeted, it wasn't cost effective to use enhanced oil recovery anymore. The plant had to shut down. When the plant's sitting idle for a year or so, unfortunately, the cost, they still have to pay their mortgage. It becomes an impaired facility. Maybe it'll restart again with the higher oil prices, but right now it's an issue, the uncertain market prices. Edwardsport plant in Indiana, Duke Energy, a fantastic project. One of the pioneering IGCC plants in our country. Construction started in 2008, went to commercial operation in 2013. But it was beset by a lot of cost overruns and schedule delays. It's in successful operation today. But if you look at any of the reports about it, you'll see a lot of people have bruises. The utility, Duke Energy, has bruises. The regulators have bruises. The ratepayers have bruises. So it's definitely an issue with respect to who's going to be responsible and handle those delays, even though it was a fantastic project. The Kemper plant, Southern Company was working on developing a new technology called a transport reactor for decades. The Department of Energy funded some fantastic research in that over the years in Wilsonville, Alabama. Well, it was ready for construction. It went to construction start in 2010, but it was a very ambitious plant with many first-of-a-kind technologies, big scale-ups, and it was canceled due to overwhelming design risks, schedule delays, and cost overruns. It was switched to natural gas. Unfortunately, that transport gas, the transport reactor, will probably never see reality anymore, which is a shame, but it shows the risk that you take. So the message, there's always risks for all stakeholders with the first-of-a-kind demonstration plant. Now, the Department of Energy has a fantastic program to look at hydrogen. Two of them are the hydrogen strategy and their plan, which just has a hydrogen shot. Their goal is that within a decade, they can have 1 kilogram of hydrogen costing $1. So it was launched just recently, and it's definitely worth reading those reports. Some of the sponsors, the projects that DOE sponsors are steam methane reforming with CO2 capture. The DOE is trying to find ways to reduce the cost of capturing CO2 with natural gas. They're working with Air Products in Port Arthur, Texas to do that. Another 2 projects are FEED, front end engineering and design studies with EPRI in Palo Alto, with Wabash Valley. These have to do with gasification of biomass. I just want to touch on that briefly, the advantage of gasification with biomass. When you look at using biomass as renewable fuel, the concept is that as long as it's sustainable, you take forests that you can replant, you take the forest, they absorb the CO2, you may emit CO2 when you're burning them, but then the new plants will absorb the CO2 again, kind of a closed-end zero emission cycle. But at the same time, if you were to take that process, put carbon capture into the process that either burns or gasifies the CO2, you're removing more CO2 from the process, you're not emitting any CO2. So the opportunity with biomass is what's called a net negative carbon system, and the DOE is sponsoring a lot of research in that area. So what does it take to move new technology forward? Let's look at the three legs of the stool. The federal government must continue to fund the development of new technologies through basic research, development, and demonstration phases. The government, through the Department of Energy, has done a wonderful job of this in the past years. I'm sure that'll continue. But just let me talk about those 3 elements. In basic research, it's basically, relatively low cost, important. You can look at a lot of ideas. Some of them are moonshots, but it does not take a lot to fund them. It goes down the funnel of development. After the basic research, you have fewer projects which look like they're viable, a little bit more money, a little bit more cost sharing from industry, and the DOE funds that. But I think the painful part is demonstration. That when you go to demonstration, you're picking winners and losers. Demonstration projects typically can cost in the tens, hundreds of millions, even $1 billion, big bucks. And of course, the government can't fund to demonstrate all these technologies. They have to pick losers and winners. When you talk with the decision makers in the DOE, that's always a quandary that they have to face as far as making sure that when they pick these demonstration projects, it's a project that they believe has a high probability of success. The government can also implement policies that address and overcome the impediments to the deployment of new technologies through either carrot and stick. A carrot meaning incentive, a stick meaning, for example, carbon tax or something like that, but that's the federal government's role. Industry needs to allocate an appropriate percentage of their corporate budgets towards R&D efforts. If you look at the history, industry typically invests much less than many industries invest much less than 1% of their revenue in R&D. And that's a shame because R&D can mean so much, and I wish that we could find a way to incentivize industry to spend more on R&D. And the regulators need to provide sufficient incentives that reward the successful deployment of new technologies, yet protect ratepayers from cost overruns and other risks. Easy to say, hard to implement, but it's got to be accomplished in order to move technology forward. So with that, I'd like to end it right now. I know I touched on a lot of topics very fast, but hopefully to whet your appetite to read the report. Of course, you're welcome to contact me or Faridun, the project manager, or the team players in Naruk with any questions. And with that, I thank you for your time. I'd like to open it up for questions.
Thank you, Mike. I told you, I told the audience at the beginning that it's a full report and it is going to raise some questions, but seeing that none have entered in the Q&A, I have a couple of questions for you, Mike. Actually, maybe one with like 15 legs to it. I recently listened to a presentation on hydrogen, and the professor from where is he? From Stanford, was adamant that you cannot have hydrogen from anything other than renewable energy, clean energy. Looking at the stats, I have my phone for PJM and ISO New England and everything. Renewables comprise a small, sometimes negligible percentage of, when I talk about renewables, I talk about wind and solar, because the only was that claim they're not polluting. Different discussion. So how, in your opinion, how feasible is it to wait for hydrogen production from renewables instead of, let's say, going with the fuel that's available right now, coal, and the technology that already exists? Should people wait for renewables to get their place in the mix, or should we say until you come back, until you grow up, I guess, then we are going to use what we have? What's your take on that?
I do not believe that it is appropriate to wait for renewables to become mature. You know, a word that I've always disliked in talking about energy is the word or. How we have to do this or that. And the challenge of engineers and regulators is to use the word and instead. To say, how can we take all our resources, renewable, coal, gas, nuclear, it's use all of them and all of them in order to meet the fantastic demand of energy in our society. I don't have the data with me, but I think it'd be very interesting. I did a study once, and the study was, if we wanted to power the city of New York alone with only renewable energy, what would it take with respect to the amount of land for wind, the amount of land for solar, or the amount of trees that had to be, forestry that has to be produced for biomass? And I wish I had the figures, but it was eye-opening and frightening that renewable energy, while it is wonderful, it's important, the energy density is not there. Fossil fuels have what's called energy density. And the energy density means you can squeeze a lot more energy into a small amount than with renewables. And it's going to take breakthroughs to ultimately get that same level of energy densities through renewables. I hope it happens. It's got to happen, but it's not there right now.
Since you mentioned the renewables and how much acreage they want, since natural gas is something I'm more familiar with, I recently was reading that per unit of energy, you need 400 times more real estate for wind generation and 170 times more for solar generation. So we're talking about vast areas of land to be taken from the current uses, whether it's forests or agricultural land. But you also mentioned something about DOE funding, and it's not a secret that the current administration has certain goals push for renewables. How likely do you believe, in your experience, and you have extensive experience, how likely do you believe how likely is it that the Department of Energy will continue funding let's say coal-based projects, like coal to hydrogen projects? Do you have any thoughts?
I have hopes. I have hopes that the Department of Energy will use that word and rather than or in their agenda of what they're funding, because there's merit in all of them. You know, when I was a CEO of FutureGen, which had $1 billion of DOE funding ultimately, that project went through approximately 6 different assistant secretaries of fossil energy, and I think it was 3 secretaries of energy, if not 4 of them. Each one of them had their own thought on how to do it. Each one wanted to tweak it this way or that way, which is appropriate. I mean, that's their job to look at their priorities, but it caused a lot of changes in directions as we went through with this project. And it's difficult with any government, how each government, each administration has its own set of priorities. And our only hope is that the decision makers will have the wisdom to stay the course and not to always change directions with too many changes in the agendas as we go forward.
Okay, thank you. And my last question, again, since I have more expertise, if you call that, with natural gas, coal also has the associated methane emissions. Is there a provision in this whole process to collect methane while mining for coal? And how much would the cost of the process increase? Do you have any estimates, any thoughts about looking into it?
I don't have good numbers on that. In fact, it's funny, the jargon within the industry is it's gassy coal. Okay, some coals are gassy, some coals aren't gassy. So it depends upon the age of the coal. I think that the methane is much more predominant with the younger coals and with the older coals. But by all means, when economical and appropriate, well, the methane has to be collected first of all for the sake of safety. But when appropriate, the methane is collected, and it does provide a revenue stream for many of the coal mines.
Yes, and also it will remove one element that would make for some folks, for most of us, coal mining not as desirable as anything else.
Right.
And with that comment, I am done with questions. Jasmine, do you have anything? I think like putting you on the spot.
I don't have anything to add, but I wanted to see if there were any questions in the audience, and if there are, feel free to either raise your hand or you can chat in the Q&A and we can have those questions answered. So I'll give folks a moment to put some thoughts in.
No, I am not seeing it.
Yeah, I don't think we have any questions. So yeah, thank you so much.
Thank you, Mike. It was like I told everyone in the beginning, it is a very detailed report, worth reading. You might not be able to finish the whole thing on the first round, on the first take, but it's the technologies are out there to help us reach our goals, and or maybe yes, maybe not. It's something that we have to all sit down and talk about. And with that, thank you again, Mike. Thanks, Jasmine. And thank you to everyone who has joined us today. I believe that the recording will be available at some point in the very near future, and so will the report. With that, thank you, everyone.
Thank you.
Great, thank you so much.